Thank you, Nicola, for your introduction, and thanks to the organizers for your invitation. So today I would like to present our work in collaboration with Julien Royer about the local decay estimate and asymptotic profile for the damped wave equation when the space behaves like the Euclidean space at infinity. So my presentation is organized as follows. First, I will give a precise definition of the wave equation in Euclidean space with perturbation of the flat metric at infinity. And second, I will review some known results on the local decay estimate of the solution of wave equation, both with and without damping. And I want to introduce our main results on the asymptotic profile and the local decay estimate of the solution of the damped wave equation. This rate of decay is governed by two different contributions: the contribution of high frequency and the contribution of low frequency. So finally, I will give some ideas how each contribution can be analyzed. So now, let us consider the damped wave equation. This equation is given by this expression as the second derivative of u with respect to t plus p of u plus a of x, the time derivative of u equal to 0. And with the initial condition, u at t equal to 0, this is a function f, and the time derivative of u at t equal to 0 is a function g. What is p here? P is a differential operator of order 2 that is the general Laplace operator given by this expression as -1 over w of x, the divergence of g of x nabla, where w here is a non-negative function and the matrix G here is positive. Here P is a general version of Laplace-Beltrami operator with variable coefficients. P is associated to a long-range perturbation of the flat metric that we have G minus identity and W minus 1 decay as x power minus rho naught for some rho naught positive. This rho naught is measure the decay of this coefficient at infinity. So at infinity we have this tend to 0, so we have G equal to identity and W equal to 1. So for G equal to identity delta G here is the delta, and W equal to 1, so P is minus delta, so P at infinity is the free Laplacian. We also introduce the damping term A. This is a absorption index A of x, which is non-negative and of short range. So we have A decay as x minus 1 minus rho naught for the same rho naught here. Here we have also that at infinity A equal to 0. So for A equal to 0 and P equal the free Laplacian, we have that this problem looks like the free wave equation. So at infinity, our model case is the free wave equation. We also defined in this asymptotic Euclidean framework the energy associated to this perturbed wave equation defined by this expression as the integral in terms of the gradient of u and the time derivative of u and the scalar function w and the matrix J. Now let me remind the local decay estimate of our model case, that is the usual free wave equation with the initial condition u naught at t equal to 0, this is equal f naught, and the time derivative of u naught at t equal to 0 is equal to a function g naught. This function is supported in the ball of center 0 and radius r. As Julien explained, the local decay of the solution of the free wave equation depends on the parity of the dimension. So we have in odd dimension, the solution vanish in any compact after finite time. But in even dimension, the situation is different. The solution does not vanish in fixed compact even for large time. But we have this properties of decay. We have that the solution at the ball decays with rate of decay t minus 2d and t2 minus 2d. So at infinity, we have that this tends to 0 for t tends to infinity, so the solution is equal to 0. So the goal of our presentation is to extend this result for the perturbed wave equation for localized initial condition and to study the rate of decay and the uniformity with respect to the initial condition. So now let me review some known classical results on the wave equation without damping. So in early 60s year, Moraut showed the first decay estimate using the multiplier method, and around the same year, Lax and Philippe obtained the exponential decay using the semigroup analysis, and they introduced the no trapping condition. This condition turns out to be essential. For example, Ralston showed that this condition is necessary to obtain the uniform local energy decay. And under this condition, Moraut and Schroth showed that using the escape function, this is a function on phase space which is increasing along the Hamilton flow. And so using this function, they obtain the rate of decay in even dimension and the exponential decay in 3 dimensions. And Burke proved the logarithm decay with loss of regularity. And there is a strong connection with the Schrödinger equation. For example, Weinberg-Melrose shows that the time-dependent problems are deduced from the analysis of the stationary problem. And similarly, Rauch, Jensen, Kato, Tsutsumi shows that the stationary problem of the wave equation, that is almost equation, is closely related to the one of Schrödinger equation. Now, what happens for the damped wave equation in asymptotic Euclidean space? So now I want to state some known results. For example, Jean-Marc Bouclet and Julien Royer in 2014 studied the local decay of the solution of the damped wave equation when the initial condition is supported in the ball of center 0 and radius r, and they obtained that the solution is decay as infinity as t with rate of decay t minus 2d plus epsilon and t2 minus 2d plus epsilon for epsilon positive. Now, if we compare this result with the decay of our model case, that is the free wave equation, where the solution decay as t minus 2d and t2 minus 2d, we remark that this result is almost optimal up to this loss of epsilon. Finally, in 2021, Jean-Marc Bouclet and Nicolas Burke succeeded to removing this loss of epsilon, and they obtained that the solution of the wave equation without damping, so for a equal to 0, that the solution decay with rate of decay t minus 2d and t2 minus 2d. So this is the same rate of decay of the solution of the free wave equation. So this result is optimal in even dimension, but it's far to be optimal in odd dimension because the solution of the free wave equation decay very fast. Now let me state our main results. So let you note the solution of our model case, that is the free wave equation, with initial condition right in terms of the initial condition of perturbed wave equation f and g, and the damping term a and the scalar function w. So with Julien Royer, we not only estimate the solution of the perturbed Ouais.
Can you explain what is the difference between the last result and the one you showed in the previous slide? Can you explain? Can you go back to the slide before?
Oui, yeah.
So it seems to me that it is the same than the first.
This result is for the damped wave equation for A different to 0.
Yes.
And this result for A equal to 0.
Yeah. But it is the same than for the wave equation, right?
Yeah, this is equation. The result of Jean-Marc Bouclet and Julien Royer for A different to 0 and the other A equal to 0. Yeah. A. So we obtain that the difference between the solution of perturbed wave equation and our model case, the free wave equation, decay with rate of decay t power minus 2d minus 2 rho 1 and t2 minus 2d minus 2 rho 1. For rho 1 between 0 and rho 0. This rho 0 is measure the decay of the coefficient at infinity. So this result allows to obtain the profile asymptotic of the solution u of t. For example, in even dimension, as the solution of the free wave equation decay with rate t minus 2d with rate t minus 2d and t2 minus 2d. So the solution of the perturbed wave equation decay with the same rate of decay. So this result is optimal in even dimension. So here we generalize the result of Jean-Marc Bouclet and Nicolas Burg to the damped wave equation. And here we have not only that the solution u of t decay with the same rate as u0, but we have the leading term of the large time asymptotic expansion of the solution u of t. We have here that u equal u0 plus this small rest. So we have that in even dimension, the profile asymptotic of u of t is u0, is the for free wave equation. So this result is for even dimension. Now in odd dimension, the situation is very different because the solution of the free wave equation decay very fast. So in odd dimension, we have not the profile asymptotic of the solution u of t, but we are able to improve the previously known rate of decay going beyond to the classical rate of decay t minus 2d and t2 minus 2d. So we obtain that in odd dimension that the solution decay with rate t minus 2d minus 2 rho 1 and t2 minus 2d minus 2 rho 1. So we have here more decay. Now we have that all this result works also for the time derivative of u. But now we are only estimate the solution u of t, but not the energy associated to the perturbed wave equation, which is right in terms of gradient of u and the time derivative of u. So to estimate to obtain the optimal decay rate of the energy, I need the similar result for the gradient of u. So this is open problem. Now I want to prove our main result from a spectral point of view. So by Fourier transform, you can write the solution formally, the solution u of t as the integral on the higher half plane of r of z, f of z, where r of z is the inverse of this differential operator of order 2, and f of z is right in terms of the initial condition of the perturbed wave equation and the damping term A and the scalar function W. And here, this operator is invertible for the imaginary of Z is positive, so in higher half plane. And this because the presence of A, this operator is not self-adjoint. As here we are interested in the time decay of the solution, so if we multiply u by t power m, so this is the same to derivative to the is the same to the m derivative of this resolvent with respect to z. And as here we are interested in the local decay of the solution, so it's equivalent to obtain decay of this solution in weighted space. So the key idea is to obtain estimate of the resolvent and its derivative in weighted space. This estimate should be uniform with respect to the imaginary part of z, and finally to tend this goes to 0. If this goes to 0, this resolvent will define this by limiting absorption principle. The main difficulties comes from the contribution of high frequency, so when z is large, and the contribution of low frequency when z is near 0. And it known that each contribution plays very different roles. Now for the contribution of high frequency, as Julien explained, this is already known. So a high frequency wave propagate along the classical rays of light. This is the solution of the Hamiltonian system. So without damping for A equal to 0, this corresponds to the no trapping condition. So to obtain uniform local decay of the energy, this rays of light should be not trapped in the region. And for the damped wave equation on unbounded domain, to obtain uniform decay of the energy, these rays of light should be escaped to infinity or pass the damping region. So under this condition, for example, Jean-Marc Bouclet and Julien Royer in 2014 obtained that the nth derivative of the resolvent with respect to z in weighted space is smaller of 1 over modulus of z. And for z large, because here is the contribution of high frequency, we have that the solution associated to the high frequency is decay very fast. So the global rate of decay is governed by the contribution of low frequency. So here for the low frequency, the geometry does not play any role. So a classical argument to prove to obtain resolvent estimate near the real axe is a Moore method. And as here we work with no self-adjoint operator, so I need a version of Moore method adapted to this no self-adjoint operator. So I want to introduce a primary version of the dissipative Moore method. So let's H is a dissipative operator. That means that this means that the imaginary part of the scalar product of H phi phi and the Hilbert space H is negative, and H equal H1 minus IV, where H1 is the real part of H and it's self-adjoint, and V is non-negative. So from Moore method, you can obtain a uniform estimate of the resolvent in this form, where A here is the conjugate to H. So it satisfies several conditions on the commutators, and in particular the important condition that is a positive commutator. So we have the spectral projector of H1 on interval J times this operator. This is positive. Is alpha here is positive. So if we have this estimate, we can obtain uniform estimate of the resolvent when imaginary part of Z is positive and real part of Z is in this interval J. Now, for example, by the Moore method, you can obtain that the limit of the resolvent where the imaginary part goes to 0, this is exists and finite in L2 space. Now, for example, for the free Laplacian, we have the conjugate of H. This is given by this generator of dilations. So if we calculate the commutator between H and A, we have that equal to H. And so for the condition on the positive commutator, so we have that the spectral projector of H times 2H for G is in R plus. So this is bigger than. So the spectral projector of H on 2G is smaller than the minimum, minimum of eigenvalue of H in the interval G times the spectral projector. And so this is larger than 2 infimum or minimum of G. And the spectral projector sphere is the same, the spectral projector. And this constant is positive. So we have that this condition on the positive commutator is satisfied. So by Moore method, we can obtain the uniform estimate of the resolvent in this form, and we can also obtain an estimate of the resolvent in weighted space if we replace A by X. Now to conclude, by applying the Fourier transform, we write the solution in terms of the resolvent. And to obtain uniform or to obtain local decay of the solution, this is equivalent to obtain uniform estimate of the resolvent and in weighted space. And here we have two different contributions. The contribution of high frequency, where Z is large. So under geometric control condition, we have that the resolvent in this weighted space is smaller than 1 over modulus of Z. So the solution associated to this region decay very fast. So the global rate of decay is governed by the contribution of low frequency. For the contribution of low frequency in this region, we have two cases. If Z near the real axe, we use the Moore method to obtain uniform estimate of the resolvent in weighted space. And if Z is far to real axe, we use the elliptic regularity of the resolvent, a generalization version of Hardy inequality. This inequality allows to convert the decay of the coefficient at infinity. This is the decay of W minus 1, G minus identity, and the damping term A to a precise rate of decay of the low frequency. Because here for the low frequency, we have that the geometry does not play any role, but the coefficients of the operator at infinity is crucial. And thank you for your attention.
So I'm sure there are questions. Some people were talking. Yes.
Sorry, it's going to be very naive probably. But when you look at your resolvent estimates, you estimate the resolvent on the real, or, well, it depends on the convention, on the imaginary and real line, it's Laplace Fourier transform. And you estimate it in weighted spaces. Well, would it be more interesting to estimate somehow the resolvent in the topology, you know, H1, L2 comp into L2 log, you know, when you don't estimate, but you cut off from both from both sides instead of taking the weighted space, and then would it improve something, or maybe you can go into the lower part of the below the real axis in this case, or
Yeah.
and your
here.
analyticity estimates. Yeah, this one. Yeah.
Yeah.
Yeah, like they do in scattering theory, they somehow. I don't know. Is it possible to completely?
Because this result in this is defined only in the higher.
No, of course. But what you could do, you could look at it analytic continuation. You could apply it to compactly supported functions, and you can gravitate it and look at the analytic continuation of the resolvent. Like, no. Yeah. Cutoff, exactly. Yeah, that's what I was saying. Yeah. Does it make sense to do it? It's a zero, okay. Okay, thank you. Okay.
Another final question?
So have you thought of considering other geometries at infinity?
So if we change this condition, so here, if we change this condition, but I don't know. But
So here you assume that you're flat at infinity essentially, but you could be, I don't know, conical or...
because here we have the model case is the free wave equation, because here at infinity this is the same, the free wave equation, but I don't know.
So, we can thank Rayan again. Thank you.